When we're talking about seeing value on objects, we need to understand how our eyes work in relationship to what particle physics of light is doing. I'm not a scientist or a biologist by any means, so this is going to be a dummy artist's account of the physics of light and the biology of the eye and its connection to the brain. But we need to have some awareness of what's going on with how light interacts with objects so we have a better understanding of value. All right, visible light is a little teeny slice of what's called the electromagnetic spectrum. The electromagnetic spectrum is a series of electromagnetic wavelengths from very short, tight wavelengths with the peaks coming very often, and that would be cosmic rays, gamma rays, X-rays. And then on the other side of the visible spectrum, you have stuff like that has longer distances between the peaks and the troughs in the waves. And so that would be microwaves, radar, radio, broadcast band. So what we see is the same stuff, made out of the same stuff that we get an X-ray at a doctor with, that we microwave our food with, that we do radar imaging or broadcast radio or broadcast television with. It's just our eyes are set up to be chemically reactive, photochemically reactive to this very tiny spectrum of those wavelengths between about 400 and 700 nanometers. The tighter wavelengths get represented to us as purples and blues, and these longer wavelengths get represented as the yellows and reds. So that's all it is. That's all color is and light is, value is when you see it. It's just how short or long the wavelengths are that your eyes are picking up. Now, if you take this visible spectrum and have it all compressed together, which is what natural light is. White sunlight has the whole spectrum in it. Hopefully you've seen this in science before. If you project that through a prism, it will break up into the rainbow. Within that, and we'll talk about this more when we talk about the eyes, within that our eyes are cued to see three primary colors. It's not red, yellow, and blue like you learn when you're learning about mixing paint. It's actually red, blue, and green are the primary colors. Red and green mixed to make yellow, red and blue mixed to make what's called magenta, and blue and green mixed to make this color, which is cyan. So if you see printed material, you'll see a CMYK color space. That's using cyan, magenta, yellow, and black. If you're like dealing with screens, like when you're looking at your computer screen, you're working in an RGB color space, and that's the red, green, blue. And then if you mix red, green, and blue together, you'll get white light. Most of the time, when you're seeing an object, it's because light's coming from a light source, whether it be natural like the sun or artificial like a lamp. It's hitting the object. The objects may be absorbing some of the wavelengths. So like if you see a red object, like you see a red rose, it's absorbing the blue and green wavelengths of light, and the red wavelength is reflecting off of it, so you see the object as red. You see the color that the object rejects. It does not hold on to red, so you see it as red because you're picking up the red wavelengths. Also, just the amount of light that it projects back off is going to determine like how bright the object looks. So if it's not reflecting much light, then it's going to be a dark object like black. Black would just absorb all the light that's coming at it, and white's going to reflect all the light. So light hits it, bounces off, and depending on how much it absorbs or does not, it hits your eye, and your eye perceives the object. Some objects also refract light. It transmits the light through itself, and they have what's called refractive indexes. This would be transparent objects, see-through objects like glass and water. So what happens there, and again, I'm not a physicist, but the light hits it, and when it hits the object has what's called a refractive index. That's how much the material bends the light. So if you got glass, it bends the light at a 34.5 degree angle. Water will bend it at 40.6 angle. So instead of the light just coming straight through the object and coming out the other side, it will bend, hit, and bend again, and it comes out not straight across from where it went in. That's why you'll get these effects like this bent, broken straw, or if you've ever dunked your arm under water in a swimming pool and it gets all fat looking all of a sudden, or it looks broken. That's because the light is coming from a light source. It's being refracted through the water. It reflects off of your skin, and then back out through the surface of the water and gets refracted again. And so there's all these bending of the image that's coming through. Now, we don't need to be all like sitting here doing the math of this and knowing the refractive indexes of things. We just need to know that there's a reason why when we're looking at an object like this cup with the bent straw, why it looks weird. We just need to know that there's a reason for that, so our cartoon brain doesn't come in and say, I don't know, man, like straws are straight, I'm going to fix that. No, there's a reason for it, and if it's going to look realistic, we'll go ahead and trust what we see, trust the shapes rather than what we think we know. And you can see a lot of these refractive and prismatic effects going on in this art piece, In Memory of Your Feelings by Mary Baumeister. There's a bunch of lenses and a bunch of spherical objects. Another thing that's interesting about something that's refractive or see-through is it will cast some kind of shadow, but it will also have that prismatic little light effect, that little rainbow going on in the middle. So you get these weird rainbows where the light's passing through, and then you get these weird distortions of the image as the light's refracted back out. So that's light. Light's bouncing all over the place. It's being projected from things, and then it's bouncing off of things. What happens is that comes to our eye. So now we're going to look at the anatomy of the eye and talk about what happens when light goes into the eye, when these wavelengths of light go into the eye. Some anatomy. The cornea, this is just a protective covering. People mistake this for the lens that helps focus. That's not correct. The cornea is just a protective covering because your pupil is a hole. Hopefully you know that. The little black spot in your eye is just a hole, and that's what lets the light into the back of the eye. But if it didn't have the protective covering, some sea creatures don't have this protective covering. They could get like a particle of dust or something, a bug stuck in there, and then they would be blind. So we evolved a cornea. Thank goodness for that. We don't have to worry about bugs flying into our pupil. The iris is a muscle. That's the pretty colored part that when you're madly in love, you say, oh my God, your big old brown eyes or big old blue eyes are so beautiful. That's the iris, and that's a sphincter muscle, a round muscle that clenches in a circular fashion, and the hole left in the middle of the iris is what we call the pupil. The iris and pupil help regulate how much light is getting in. I'm sure you've all experienced this. You've been like sitting in a dark room all day and you go out into a bright sunlit light and it like hurts to look. That's because your iris has really relaxed while you're in the dark room and really opened the pupil up, and so it's letting a lot of light in. And you go outside and all of a sudden it's super bright out, and so your iris like hasn't contracted the pupil yet and too much light's getting in. And then as you're out in the sun for a minute or so, the iris will start to contract, it will start to clench, and there will be less light getting into your eye, and you're no longer like blinded by the light. The lens is actually behind the pupil. It's a dense body of cells that are able to stretch, and they have these suspensory ligaments that attach to them that are like little muscles here, and then they grab onto the lens, and to help you focus, they'll pull tighter or loosen up to change the shape of the lens. So as you're looking at something close and you focus, and as you look at something far away, the suspensory ligaments are grabbing and releasing. So if your eyes are getting tired, there is a lot of muscle motion going on in there. The iris is closing and releasing. The suspensory ligaments are pulling on the lens, and you are getting a workout in your eye. The lens also, those cells that are in the lens, they don't replenish. Most cells in our body, as they die, they slough off, we get rid of them, and then they replenish with something else. These ones don't go anywhere. So as they die, they just start to turn into cloudy dead cells, and that's why we start to lose vision as we get older, is those dead cells get in the way. And if it gets too bad, you'll get cataracts, and you would have to go have all those dead cells removed. So all of these mechanisms up front are here to focus and control how much light comes back to this back part. This whole thing here is like a screen of photoreceptive cells called the retina. At the very center of the retina, a very teeny tiny spot, that's the high resolution part of your vision. Everything else is low resolution. So here is where pretty much all of our color receptors are. They see high resolution and color. We'll look at those more closely in a minute. And then all around here are the rods, which are low resolution, and they're mostly meant to detect value and motion. Here's where we detect color. And if you hold your thumb out in front of you, like extend your arm out, the size of your thumbnail is about in your visual field, like, everything that you can see all the way out into your periphery. The size of your thumbnail is about how much the fovea actually covers. So when your eye's doing those saccadic motions that we've talked about, all of the information that the rods are providing it control the eye. A lot of this information doesn't even go back to the brain, and it's just telling it where to saccade, which is to point the fovea. And then the fovea picks up those little bits of information, and that gets sent back to the brain for the high definition color processing. Rods send information back to the brain as well, but some of that information just loops back into the eye. So if we've all experienced it where someone walks by and you just turn your head to look before you've even realized that you're turning your head, and then they kind of give you that, like, why are you looking at me look? It's like, well, because some of the nerves in my rods just redirected right into my eye. They never even went to my brain, and I was turning to look at you before any information went from the eye through the optic nerve back to the brain. So we also have that. We have the optic nerve, which runs out and actually comes up in here and gets in front of the retina. It blocks off some of the light from our retina, and that transmits all of the electric signals that the retina creates back to the brain. And you can actually, if you play around with your periphery, to the left of your left eye and to the right of your right eye, if you move your hand around off to the side, you'll be able to get it in the blind spot where it disappears for a second. That's just where the optic nerve is blocking off the retina, and your brain is just so used to seeing the optic nerve and the shadow of the optic nerve in the way there that it has decided to edit it out. So that's an interesting thing. There's also a lot of blood vessels and a lot of nerves. All the nerves that connect all of the rods and cones are actually in front of the retina. So our brain is constantly filtering that out. And then this whole body of the eye is filled with like a salty liquid. And if you've ever seen those floaters and stuff, that's those things floating around inside of the salty liquid. And your brain, again, is usually just editing that out because it's learned that it's not useful information. So a lot of what you see is just your brain getting rid of things and filling in their place what it thinks should be there. Another really weird thing is that as the light comes through the pupil onto the lens, it's focused in such a way that it shifts upside down by the time it hits your retina. So obviously the further away an object is, the smaller it's going to show up on the retina, and the bigger it is, the bigger it's going to show up on the retina. So that's why objects look smaller as they get further away. But much more strange than that is that if you were to take a photograph of how this light showed up on your retina, it would be upside down, and your brain just learns it's not very useful to see the world upside down, and so it shifts everything back right side up. And we're involved, our eyes and our brain are involved in this really bizarre, complicated dance where our eyes are providing some information, and then the brain's just making a lot of decisions and assumptions based on what it thinks it wants to know. Now, looking more closely at the retina, right? This is like way back here, looking at this screen of photoreceptive cells. There are two different kinds, well, technically 4 different kinds of cells, but 2 different groups. There's rods, and the rods are mostly located in the periphery. There's some in the middle. And there's cones, and cones are mostly located in the middle around the fovea, and there's just a few of them on the outside everywhere else. Those are all back here. That's like along the back. Those are back here. The light's out here. The actual blood vessels and nerves that connect them all together are in between the light and the cells. So that's what I'm talking about. Like the light's here. You've got all the blood vessels and the nerves that connect everything and collect the information. They're in the way of the light, and then the light comes back here to the rods and the cones. So our brain edits all that out. The rods are receptive. They're highly sensitive to changes in value, to changes in light and dark, and they're really sensitive to motion. They help us edge detect. They're the basic navigational system that we've got, and they work really well at night. We've got really good night vision. We just don't ever get to see it because there's lights everywhere. The cones are what help us see color, and there's 3 different types of cones with 3 different types of chemicals that are called rhodopsins. The different rhodopsins respond differently to different kinds of light. So you have a cone that responds to most of the light coming into the eye, but it responds most aggressively to blue. And then you have another one where the chemical responds most aggressively to the green light wavelength, and then another one that responds most aggressively to the wavelength of light that we see as red. That's why those primary colors of light are red, blue, and green. Now, someone like me who's red-green colorblind, there's a mutation in the rhodopsins that I have where they don't respond differently enough to red and green. They respond about the same to the red as they do to the green, and so I get a little bit confused. I can still tell the difference a little bit, but it's not as dramatic as it is for other people because they're responding to more similar wavelengths of light than most people. That also shows up in some women because it's a mutation on the X chromosome. Men only have one X chromosome, so I happen to have a mutation on my X chromosome that alters one of my rhodopsins and one of my cones. Women can have that mutation as well, and since they have 2 X chromosomes, it can happen where women actually are what's called tetrachromes, and they'll wind up with 4 different cones. And then really, that's like 12% of women have that, and then within that 12%, a very small subset of them have a 4th cone that's dramatically shifted enough in its receptivity that they see about 100% more nuance and color than the rest of us. I don't believe that they see more colors. I mean, maybe, I don't know. I'll never know. I see way less colors. But their sensitivity to color is at least 100 times more than other people. So some of the ladies in class, especially if you know that there's a male with color blindness in your family and you're especially sensitive to color, you have real strong reactions to color, you may be a tetrachrome who has you're a superhero with a special 4th cone in your eye. For us, this is most important because we need to just think about how light bounces off an object. One of the major reasons we see things as 3-dimensional is how much light is bouncing off of it or not, how our eye is receiving the light. So if we look at this image here, same kid in both pictures. On the left, there's an overall lighting. It's overexposed. It's pretty much just reflecting light back at us from everywhere. And you'll see this a lot in fashion photography because what it does is it gets rid of all of the sense of 3-dimensional sculpture of the face. It gets rid of all the blemishes, and it compresses everything down to like that emoji that we want of eyes, nose, and mouth, and edge. But it doesn't give us any volume, surface information. In art and drawing, we're usually looking for the opposite of that, which is where we have high contrast between the lights and the darks. We have good, like here we have lighting above head. It creates really deep shadows. You've got gradients moving from really dark into the light, into the midtones, into the darks again, all the values in between. This is what we want in our drawings. We want a really full range of values. We don't want just darks around the shadows and lights everywhere else. We want all of the gradients in between. A lot of the advice you're going to get from me in this later half of the semester, it's like, well, what do I need to do next? More values, more gradients. What do you mean more values, more gradients? Well, there's an infinite number of values here. Like, how many of them can you get? A lot of students have a hard time ever getting more than 4, 5, 6 values. We need that to describe form. Here you'll see we see the pockmarks in his face more. We understand his cheek better. We see how deeply set into his face his eyes are. There's just so much more information about the volume of his face when we have a high range of value. So some vocabulary about how to refer to light as it's showing up on a form so we can talk to each other about this. The highlight is the part of the object that's just facing right towards the light. And it's not this really extra bright circle right here. I'll make a distinction about that later on. But for right now, just whatever part of the object's directly facing the light's in highlight. Now, if it's a continuous object like this sphere here, and this is an ideal situation where you just have one light source up here and no other light in the room, we'll have this is in the highlight. Then we have these transitional lights, transitional middle values. That's a gradient that's moving across the object. As you get back to the darkest part of the object, you'll have the core of the shadow. Now notice this object has a local value of white. That just means if I hold the object up and I say, what color is this? You'll tell me it's white. So on a white object, the core of the shadow is probably not going to be black. On a black object, the highlight's probably not going to be white. It'll probably be 40-50% gray. Same here, the darkest it's going to get, it's like 50% gray. So the core of the shadow would just be the darkest part. This core also isn't the part of the object that's furthest away from the light. That's a misconception that most people have. The part that's furthest away from the light usually is catching some reflected light. So here the light's hitting the table and it's bouncing off the table, scattering in all different directions, and it's illuminating the back side of the object. So you'll get what's called reflected light along the back here, and we actually move back to like maybe a value like about this shows up on the back. Doesn't get as bright as a highlight, but it gets brighter than the core. So the core of the shadow is usually a little bit away from the back, and then you need to pay attention to the reflected light. None of these have a sharp edge. You need to be really good at gradients to render these transitional lights. Where you do get a sharp edge is on a cast shadow, and that's like our shadow that follows us around. This is where the object just cuts a hole out of the light that's coming at it and leaves its shadow. But even within the shadow, there's more light catching it out here, so you'll get a gradient from a little bit lighter here to quite a bit darker where the object's blocking off most light, and then a little bit lighter out here again. And you can see all of that better on a setup like this. So you have this area that's in the highlight, this really bright spot here I'll talk about on a different lecture. We have the transitional lights. You'll come to the core of shadow. This is called the penumbra of the shadow, where it changes from dark to light really quick, but it's not a sharp line. It's one of those quick but fuzzy gradients that we've got, and that's why we need to be so good at rendering them. And you'll see the penumbra softens up down here. Doesn't stay as quick all the way through, but it's still not a crisp, solid edge like the cast shadow. The penumbra's always got a bit of fuzz to it. Then you'll have the core, which is the darkest part. You'll get another really dark part here, and some reflected light up through there. And then the cast shadow has that really crisp, sharp edge, but it still has a gradient lighter here, darker here. Alright, so those are the basics of the terminology we're going to use when we talk about value.